In this video, we're going to be talking about what the different types of intermolecular forces are and how to identify which types are present in a particular molecule. All right, so to start off with, we should probably get a definition of an intramolecular force and an intermolecular force. Intramolecular forces you're already familiar with. These are the bonds between atoms, so your ionic and covalent bonds. Right, so inside the same molecule means they are intramolecular. Intermolecular forces are attractions that take place between different molecules, right? So if I had one sugar molecule and another sugar molecule, those molecules will have an attraction towards each other, and those are intermolecular forces. Now, intermolecular forces always affect potential energy, so please keep that in mind, especially later on when we start talking about condensed phases and how to kind of compare the different types of forces. Right, now, one thing to keep in mind with intermolecular forces is that on their own, they're nowhere near as strong as a chemical bond is. But if you get a large number of molecules nearby, they add up fairly quickly and they can have a very large effect on certain properties like melting point, boiling point, viscosity, vapor pressure when we get to that. Right, so individually they're much weaker, but collectively they add up really quick. And one thing to keep in mind is that being able to identify dipoles and the strength of dipoles is going to be really important here. Right, so again, intermolecular forces are attractions. They hold molecules together. If you're holding molecules together, it becomes harder to melt or boil them because you have to separate molecules in order to accomplish those phase transitions. It also leads to what are called lower vapor pressure. Vapor pressure is the pressure generated by the molecules that can break free and become a gas from their liquid state. Right? So if you have a puddle sitting on the ground, some of those water molecules will always have enough kinetic energy to break free of all the attractions holding them together and become a gas. The stronger the attractions are, the harder that is to occur. Right, so our first force is what's called dispersion force. You'll also see this referred to as London dispersion occasionally. Dispersion force is based on what's called a temporary dipole or an induced dipole. Right, because what happens is that since electrons are in constant motion around a molecule, it's quite possible that you will get a distribution of electrons where one side of the molecule has more electrons than the other side, leading to that side being more negative, the other side being a little bit more positive. These are temporary because as the electrons move back and forth, they'll go away, they'll get stronger, they'll get weaker, they'll change directions, right? But they will almost always constantly exist in a sample of a substance. Now, the way that you tell how strong a dispersion force is by what we call how polarizable the electron cloud is. Right? Electron clouds are more polarizable, which means polarizable just means easier to generate separations in charge. Right? So an electron cloud that has a lot of electrons makes it very easy to get those very temporary, like +1, -1, +2, -2 side charges. Right, so the more electrons something has, the easier it is to create that imbalance. Also, the physically larger the cloud is, the easier it is to create that imbalance as well. Right, because then you have those electrons spread out over a much larger volume, basically. Right, so the strength of dispersion force will be based on how polarizable the electrons are. Now, electrons can take a little while to calculate, right? So a good approximation is molar mass. Molar mass correlates very well to the number of electrons in a molecule. Just beware that when you explain dispersion force, you don't explain it by this substance has a higher molar mass. You explain it by this substance has more electrons, or this substance's electron cloud is more polarizable. Right, but molar mass is a good approximation, and the trend, we're going to have two different trends. We're going to talk about the first trend is what if the molecules have different molar masses, and I mean noticeably different, versus what happens if the molecules have similar molar masses. Right, so if there's a large difference in molar mass, that means there's generally going to be a large difference in the number of electrons. The heavier one will have more electrons, which means the cloud is more polarizable. Now, if they have a similar molar mass, you're going to want to look at size of the molecule, right? So surface area. The more surface area, the more polarizable the cloud's going to be, the stronger the dispersion force. Right, so I have an example of these coming up on the next couple of slides. So this right here is an example of number of electrons showing you how polarizable something is. These are our noble gases. And as we notice, as you increase the number of electrons from helium to neon to argon to krypton and so forth, the boiling point of the substance increases. This happens because xenon has a much more polarizable electron cloud because it has more electrons than helium does. Since it's more polarizable, we can generate larger charges. Those charges stay around for a bit longer, which means the dispersion force that holds xenon molecules or xenon atoms together is much stronger than it would be in helium. Right, so that's why xenon has a higher boiling point. Right, so again, higher molar mass, more electrons, higher boiling point, because atoms will get stuck together a little bit more. Similarly, if we look at shape, so we have, this is all pentane, so C5H12, all three of these, and we have three different types of pentane. We have what's called N-pentane or normal pentane, which is the 5 carbons in a straight chain on the right. That has the largest surface area because it takes the shape of a cylinder. We also, on the left, have neopentane, which is where you have 3 carbons left to right, one above the center, one below the center. This is a very small surface area because it forms a more spherical shape. Remember, spheres have lower surface area than cylinders do. Right, so because the sphere has a lower surface area, its molecules exhibit less dispersion, so less attraction, which means it's easier to boil them, which means it has a lower boiling point. So neopentane boiling point a little under 10 degrees, N-pentane boiling point a little over 35 degrees. Right, and then you have isopentane, which is kind of in the middle, and its boiling point is also in the middle of those two because larger surface area than neopentane, but smaller than regular pentane. Right, so that's dispersion force. Our next force is what's called dipole-dipole. Here, in this case, this is because we have permanent dipoles in a polar molecule, right? So HCl, the hydrogen side of HCl is always positive. The chloride side of HCl is always negative. And because of that, if you get HCl next to another HCl molecule, you can arrange it so that the negative chlorine on one atom is next to the positive hydrogen on another, and that creates an attraction. Right, so the oppositely charged ends can attract each other. If you've ever used an Etch-a-Sketch and you saw like how the magnet, if you leave it on there, it'll attract a few little grains of iron, and then that will attract more and more and more, and after a few minutes, the entire bed of iron is sitting up onto the surface of the glass. Same effect. Right, the strength of dipole force is proportional to the polarity of the molecule. The more polar the molecule is, the stronger the dipole force. So something like HCl is a very polar molecule. That means it has a very large dipole-dipole force. Now what I have here is the boiling point example. These are different nonmetallic hydrides of groups 14 through 17. And what we notice, right, we notice that, again, dispersion, heavier molecules, higher boiling points, right? So H2SE is probably the heaviest of these molecules. It has the highest boiling point of the ones that aren't H2O, HF, and H3, right? Because it has the most dispersion. Also, because H2O, HF, and NH3 are polar, their dipole-dipole force causes an additional attraction, which means the boiling point should be very high because they're very, very polar molecules. But here's the question I have to ask. HF is much more polar than water is. So why does water have a higher boiling point than HF? Right? So why is that? There must be something else in play here. And the boiling point, if you notice, it's a very large difference in boiling points, about 85 degrees. Right? The reason for this has to do with our third intermolecular force, which is hydrogen bonding. So when you have very electronegative elements, you can form very strong polar molecules, right? Well, if you have a hydrogen that is bonded to a nitrogen, oxygen, or fluorine, that attraction is so strong that we give it its own intermolecular force name. We call it hydrogen bonding. So any molecule with an NH, OH, or FH bond will hydrogen bond to any other molecule that has an N, O, or F in it. Right? Hydrogen bonding, and we'll get to this in the next video, is the strongest type of intermolecular force we're going to deal with individually. And if you want a little mnemonic as to how to remember when you're going to have hydrogen bonding, just remember to think back to this classic 80s song and remember that hydrogens just want to have fun. All right, so these are our three basic intermolecular forces: dispersion, dipole, dipole, and hydrogen bonding. You should be able to identify the forces that are present in a molecule just by looking at its Lewis structure. All right, so that is it for this video. I will see you guys in class.